This example you'll recognize. We've looked at this before, and we went through and we solved and determined the voltage and current unambiguously. There's no unknown complex constants involved here, since we have a complete circuit attached to a source on one end and a load at the other. Went through and applied boundary conditions and determined unambiguously all these values, including the value of load current and load voltage. Again, we did this by applying boundary conditions, which is the general solution, and of course always works for any problem. For some problems, however, some circuits, we can use a few tricks to kind of simplify the analysis to get the answer quicker than by applying explicitly a set of boundary conditions that give us multiple equations with multiple unknowns. And so this is one of these cases, and the reason that it is one of these cases is because the lengths of transmission lines, if you look at them, are lambda over 4. And so this is one of our special cases that we deal with, and this is one where we can apply equivalent circuits to analyze the structure in a quicker manner. So we're going to collapse the circuit. We're going to take the circuit and collapse it back toward the source to come up with an equivalent circuit. And these are things that we've done before to try to find the input impedance for these special cases. We look at the first section here at the end of our circuit, and what we can look at this is a two-port device, which is an impedance transformer that transforms 50 ohms into some new input impedance. Fortunately, since this is a lambda over 4 length, quarter wave length, we can use the special case, and the calculation is simple and straightforward. 25 squared divided by 50 is 12.5. Now, I would point out that since 50 is twice the size of 25, then the resulting input is half the size of 25. All right, so that's how the geometric application works here. If this is twice as big as this, then this is twice as big as that. So we didn't really need to go through and do the calculations. We can immediately find that the input impedance is half 25 ohms. So we continue to collapse our circuit to find an equivalent circuit. Now we've replaced the transmission line that's terminating the load here on the right side of the circuit with its equivalent circuit, an input impedance of 12.5. And now we're going to again go through and look at this length of transmission line as an impedance transformer that transforms 12.5 ohms into a new input impedance, which is 800 ohms. And again, we can use, because it's a special case, the equation to find 800 ohms, or we can just recognize that 12.5 is 1/8 of 100, and therefore the input impedance must be 8 times 100, or 800 ohms. So we've replaced our entire circuit to the right of the source with an equivalent circuit, its equivalent circuit, and that equivalent circuit has an input impedance of 800 ohms. And notice I have a mistake here. This should be 800 ohms, not 12.5 ohms. And so this is our equivalent circuit, source 50 ohms, and then an 800 ohm input resistance or input impedance. So notice the source, of course, has not been affected by the transformation. Just the two transmission lines and this load have been replaced with an equivalent circuit of 800 ohms. Again, there should be 800 ohms here. But this part is the same as the original circuit, and therefore the current coming out of this source and the voltage at the output of the source is going to be unaffected by this transformation. In other words, we can replace all this with an equivalent circuit to find these two values. V out can be found with voltage division, and I have the right values of 800 here, so this is the correct value for the output voltage. Likewise, from Ohm's law, we can determine I out, where again I have the right value for 800, so this is the right answer. What do we do now? Our problem statement asks for the values of the load current and load voltage, not the values of the source current and source voltage as we just determined on the previous page. So what do? Well, we took the circuit and of course we crushed it into an equivalent circuit to find the source current and voltage. Now what we're going to do is expand it back out. So I call this the accordion method. We crush to the source and find a first value with an equivalent circuit, and then undo the process, gradually expand it back out. And when we do that, we're going to take the first result and sort of propagate it or transfer it from one side of the circuit to the other, one side of the transmission line to the other. Again, as we expand out further, take our answers and propagate down the source, or down the circuit rather, until finally we get the answer that we're looking for, the load current and load voltage. The first step then of this accordion process is to pull back the circuit so that we reveal the first explicitly reveal the first length of transmission line. Notice this transmission line is terminated by a load which is 12.5 ohms, and this is the equivalent circuit for the second transmission line that's terminated with the load at the end. So we're still retaining part of the equivalent circuit here, but now we've revealed this physical structure, which is the correct physical structure. Of course, the important thing is that we know what the current flowing into that transmission line is and the voltage across the end of that transmission line from KCL and KVL. So from KVL we conclude that the voltage here at this location on our transmission line, this is the total voltage at this index, must be equal to J16, because that is the output voltage from the source that we just calculated. Likewise, the current here at the beginning of the transmission line at Z is equal to lambda minus lambda over 4, that total current must be equal to IN, the value of J.02 that we just calculated there. So now we have the value, two values on our transmission line. And remember, on our transmission line, we have two unknown, every transmission line, we have two unknown complex constants. If we know two values on the transmission line, then generally we can determine those two complex constants. Two equations, two unknowns. So we have those two equations. Now we can solve for those two unknowns. If we take our telegrapher equation solution for the total voltage on that first transmission line and carefully evaluate it at a location, a numeric location of Z is equal to minus lambda over 4, be careful with the complex exponentials, what we'll find is that will be equal to this result. And so we have the voltage on the transmission line in terms of the two complex unknown wave amplitudes, V0 plus and V0 minus. We know this result must be equal to J16 by KVL. Likewise, for the current, when we evaluate it at the beginning of the transmission line using the telegrapher equations, we get this result for the current, and being careful to make sure we get the signs right when we evaluate the complex exponential. Take these two equations and do a little algebraic simplification, and we have these two results, two equations and two unknowns, and we can quickly determine now the value of our unknown wave amplitudes. V0 plus is 9, and V0 minus is minus 7. Again, these are complex numbers, a real value of 9 and imaginary part of 0. Or a magnitude of 9 and a phase of 0, for example. These are exactly the same results as we did before, and by as before I mean when we did this same example using boundary conditions and solved it using boundary conditions, where we ended up with 4 equations and 4 unknowns. Here we are able to directly determine 2 of the unknown wave amplitudes by solving simply 2 equations and 2 unknowns, and that's the benefit of the accordion, is we sort of take care of 2 unknowns at a time, as opposed to a very large pile of algebra that we have to fight through to get simultaneous equations. But these are exactly the same results, and of course they must be the same results. The circuit itself cares not about how we analyze it and what technique we use. If a technique is valid, it must give the same results as any and all other valid techniques. Now that we solve for the 2 unknown wave amplitudes, V0 plus and V0 minus, we can determine any and everything along that transmission line. We can determine voltages anywhere, currents anywhere, impedances anywhere, line impedances anywhere, reflection coefficients, plus wave, minus wave. Again, once we have those 2 unknown constants, everything about the transmission line now becomes known to us. What is it that we're interested in? Well, what we're interested in this case, to solve this problem, is specifically what are the values of the voltage and current here at the end of the line, at the value Z is equal to 0. Again, since we know now completely unambiguously the total voltage and total current as a function of position Z, we simply insert Z is equal to 0 into those equations, and we get these results. And since we know V0 plus and V0 minus, we find the value of the total voltage and total current here at the other end of the line at Z is equal to 0. Again, these are complex values. that result. Notice these are exactly the same results that we calculated earlier in the earlier example, as they must be. Now we expand our accordion one more time. We're going to take that equivalent circuit, which was the load at the end of the first transmission line, and expand it out into the complete physical circuit. No more equivalence for the circuit any longer. And so what do we do now? Well, we know the current and voltage at one end of the transmission line and of the first transmission line, and we can use KVL and KCL to immediately then determine the currents and voltage at the beginning of this second transmission line. From KVL, we know these two voltages are equal to each other and therefore equal to 2 volts. These currents are equal to each other and therefore equal to 0.16 amps. Again, these are complex numbers that we have. What do we do with this? Well, once again, we have on our second transmission line, we have two equations. We have 2 points where we know, one point where we know the total voltage, it's equal to 2, and at that same point we know the total current, it's equal to 0.16. If we have 2 equations, then we can solve for the 2 unknowns. What are the 2 unknowns? They're the unknown wave amplitudes on this second transmission line. Again, if we know 2 values on our transmission line, then we can solve, generally speaking, to find the 2 unknown wave amplitudes, V0 plus and V0 minus. Once we have those 2 values, we know everything and anything there is to know about that transmission lines. All problems are solved at that point. So if we take the general telegrapher solution for that second transmission line and evaluate Z is equal to 0, we get this result, of course, V0 plus V0 minus, and this is for the transmission line B there. For the total current at Z is equal to 0, we get this result, and of course we know that result must be equal to 2 volts by KVL, and this result must be equal to 0.16 amps by KCL. 2 equations, 2 unknowns that result from these 2, and we can combine them with algebra, simple algebra, to determine the unknown wave amplitudes for that second transmission line B, and that should be a B there, not an A. The values are 3 and minus 1. That is the same result as we got before in the earlier example for the same problem, where we approached it in a different way using boundary conditions exclusively. So now that we've determined the 2 wave amplitudes of V0 plus and V0 minus for that second transmission line, once again we can determine any value at any place on that transmission line. The values that we desire are the value of the total voltage here at the end of the line at Z is equal to lambda over 4, and likewise the current here at the end of the line at lambda over 4. So now that we know our wave amplitudes, we know the total voltage and total current explicitly, and we can evaluate it at lambda over 4, and we get a value of minus J4 volts. And the current, likewise, we evaluate that current expression in the telegrapher equation using the values of wave amplitudes we just determined, and that gives us a minus J.08 amps. Notice these are precisely the same results as we achieved or determined in the example where we used exclusively boundary conditions to solve the problem. The last step is pretty straightforward and hopefully self-evident. We want to find the load voltage and load current, and by KVL and KCL, the load voltage is equal to that voltage at the end of the second line, which we know is minus J4. The load current is equal to the current at the end of the second transmission line, and then we know that's equal to minus J.08, and therefore by KVL and KCL we get our result for load voltage and current. And these are, again, exactly the same results as we did earlier, where we used boundary conditions exclusively. So this accordion method that we just showed allows us to independently determine the 2 wave amplitudes for each transmission line. We had 2 equations and 2 unknowns, which we had to solve twice. This is in contrast to the exclusively boundary condition problem, where we went through and had 4 equations with 4 unknowns and had to provide the algebraic solution to that. That may not seem like too much of a difference there, but if we start to have multiple sections, 3 or 4, certainly that it gets much easier to do this expansion, this accordion. And this is something that we'll use quite a bit. The reason is because in most microwave circuits that are useful, we'll find links of transmission line that are associated with our special cases, lambda over 4, lambda over 2, and so frequently we can apply these special cases to crush our circuit into an equivalent circuit, easily find a current and voltage associated with the source, and then propagate that answer back as we expand out the accordion. And so we have a series of simpler mathematical operations as opposed to sort of one large mass of equations that we have to solve for. So again, I think the accordion method is a simpler method. You can use either one. You get the same answers, as I tried to emphasize here. But if you have special cases, I think the accordion method is simpler.